In this video, we're going to be talking about exercises from 1.6, and we'll be determining continuity. Continuity has a three-part definition that I will write up here as we get started. So the first part of the definition says that if f, let me just write this part, if we say f of x is continuous at x equals c. Notice we have to have continuity at a point. This is what we mean. So part one of the definition, f of x is defined at x equals c. You could say that or as f of c exists, right? Part two, the limit of f of x as x approaches c equals L. The limit exists. And then the last thing is going to be that those two things have to equal one another. So it's getting crazy. The limit and function value are equal. So the function is continuous. Well, let's just say it's discontinuous, is not continuous at three types of things. 1, 2, 3. So vertical asymptotes, holes, and jumps in the graph. Jumps really usually only happen with piecewise defined functions. There's going to be some functions that are absolute value functions that are piecewise functions in disguise. So we'll look at that, but let's just deal with these notes first, and then we've got several problems for this section. We'll have some of them with the function, and some of them we'll have a graph to look at. So in general, a function is continuous on its domain. There are a few exceptions, but in general, that's going to be what we're looking for. Is when we ask you for where a function is continuous, you can almost think of that as the question from pre-calculus: what is the domain of this function? So let's go ahead and get started here. And number one asks me about f of x is equal to 5x cubed minus x squared plus 2. So if I ask you where that function is continuous, it's continuous on its entire domain. So we would just call that a continuous function, right? And the question here is determine whether the function is continuous on the entire real number line. The answer is yes, it is. Yes, it is continuous for all real numbers. How do we know that? Because this is a polynomial function and all polynomial functions are continuous for all real numbers. So let's look at number 3, and it is f of x is equal to 3 over x squared minus 16. And it is not continuous everywhere. So it's discontinuous at x is equal to -4 and 4. These are vertical asymptotes, so no, it is not continuous for all real numbers. Let's look now at number 5. And we have f of x is equal to 1 over 4 plus x squared. And you might need to consider the graph of that function before you can answer that, but it looks something like so. I'm not great at drawing this, but it's kind of bell curve shaped if you've seen a normal distribution. And its maximum point up here is going to be 0, 1/4. So I exaggerated this quite a bit so that you could see what's going on here. It's going down and getting close to y equals 0, going down and getting close to y equals 0, but there's never any vertical asymptotes, there's never any holes. I can stick in any x value that I want and square it and add it to 4, and I get a non-zero denominator. It's defined here for all real numbers. So yes, it is continuous for all real numbers. Because a rational function is continuous on its entire domain. And the domain of this rational function is all real numbers. All right. Let's go ahead and look now at finding continuity from graphs. So I'm going to look at number 11 from the textbook. And give me just a second to show that one to you. All right, there we go. And we can see that we have a vertical asymptote here at x equals 0, so discontinuous at x equals 0. We have an oblique asymptote or a slant asymptote here. Probably it's something like y equals x, but that really doesn't matter in terms of x values that I can't plug in. So I see the function there. I see that x is not allowed to be equal to 0. So that's my only discontinuity. And so my complete answer here when they ask me for intervals for which it is continuous will be negative infinity to 0, union 0 to infinity, which is its entire domain. So, but it violates part 1, reasons that it's discontinuous. Part 1 of the definition is broken. Part 2 of the definition is broken. We can't have part 3 without part 1 and part 2. So it's just broken that there is no function value, there is no limit. This was number 11. Let's go ahead and look now at number 13. I'll clear this. And number 13 here is right here. And notice this hole that's right here in the graph. It is continuous everywhere else other than x equals -1. So discontinuous at x equals -1. There's a hole there. And so we're continuous on negative infinity to -1, union -1 to infinity. And which part does it violate? It violates part 1 of the definition that I gave you, that the function value has to exist. The limit exists, but the function value does not exist. All right. Let's go ahead and look now at number 17, which is not a picture again. And any kind of instructions for me to tell you where it is continuous, and anywhere where it's discontinuous for me to tell you why. So in 17, we have f of x is equal to x over x squared minus 1. That's x over x plus 1 times x minus 1. So my domain is going to be negative infinity to -1, union -1 to 1, union 1 to infinity. And so that's where it's going to be continuous. So it's continuous on negative infinity to -1, union -1 to 1, union 1 to infinity. It's discontinuous at x equals -1 because of a vertical asymptote, and that violates parts 1 and 2 of the definition, and discontinuous at x equals 1 because it's also a vertical asymptote, and that also violates parts 1 and 2 of the definition. Let's move on now to question number 21. F of x is equal to x minus 5 divided by x squared minus 9x plus 20, which is x minus 5 over x minus 4 times x minus 5. Those x minus 5s will cancel and reduce down to 1 over x minus 4 as long as x is not equal to 5, because 0 over 0 does not become 1. So I have to keep this restriction here. The f of x is the same as 1 over x minus 4 as long as x is not equal to 5. So there is, it's discontinuous. At x is equal to 4. That's a vertical asymptote there that still remains in the denominator, and that violates parts 1 and 2 of our definition. It's discontinuous at x equals 5 because there's a hole in the graph there, and that violates part 1 of our definition that the function value has to exist. The limit will exist there, the function value will not. So it's continuous on negative infinity to 4 union 4 to 5 union 5 to infinity. Let's look now at number 25 from the textbook. Number 25 is f of x is equal to the square root of x plus 2. So we're going to say, for the purposes of this course, that radical functions are continuous on their entire domain. I know they can only be continuous from one side at their vertex. That's okay. So we're going to say that it is continuous at its vertex, because as soon as I put my pencil down to start drawing that point, I can draw the rest of it without picking my pencil up off the paper. So different textbooks will argue about that and say that it's only continuous from one side because there's no behavior from the other side. Don't worry about that. In this textbook, you say that this is the type of function that's continuous on its entire domain. So the domain of this function is that x needs to be greater than or equal to 0, which can be written as 0 to infinity here. And so this is going to be continuous on its entire domain, 0 to infinity, and radical functions are continuous on their entire domain. Okay. Let's look now at number 27. And we have a piecewise defined function for number 27. So we have the possibility of a jump discontinuity. I'm not saying we will have a jump discontinuity. We just have to think about that since we see a piecewise defined function. F of x is equal to negative 2x plus 3, as long as x is between negative 1 and 1 included on both sides, and is equal to x squared when x is greater than 1 and less than or equal to 3. Why did I write x on both sides there? When x is greater than 1, but less than or equal to 3. There we go. So my question here, I know that this line is continuous because it's a polynomial degree 1. up to its endpoint. I'm not sure what's going on at its right-hand endpoint, but I know everything from -1 up to 1 is continuous. I know that this polynomial x squared is continuous on its domain right here. My question is if these two pieces touch each other at the right-hand side and the left-hand side, do they connect so that I can draw both pieces together without having to pick my pencil up off the paper? So the limit of f of x as x approaches 1 from the left, this left-hand limit, is equal to -2 times 1 plus 3 is -2 plus 3 is 1. The limit of f of x as x approaches 1 from the right, I'm coming from the right-hand side here. I'm going to stick 1 into the bottom piece. 1 squared is 1. And yes, they do equal one another. So f of x is continuous on the entire domain of, watch out here, it's not -infinity to infinity, it's -1 to 3 because I have a lower bound and I have an upper bound here. So let's look now at number 29. It's also a piecewise defined function, so we also have to be thinking about the possibility of jumps in the or breaks in the graph somehow. So f of x is equal to 4 minus 2x, x less than or equal to 2, and x squared minus 3, x is greater than 2. And so we're going to try that same idea of take the limit from the left and the limit from the right. Limit of f of x as x approaches 2 from the left. We're going to stick it in as x comes from a number less than 2. We're using the top piece. 2 times 2, that's 4 minus 4 is 0. And as I come at 2 from the right, a number a little bit bigger than 2, I'm going to be using the bottom piece here is x squared would be 2 squared minus 3. 4 minus 3 is 1. These are not equal, so we're discontinuous at x equals 2 because it violates part 1 of the definition. The limit will not exist. I just checked the limit from the left and the limit from the right. They're not equal, so the limit doesn't exist. The function value exists. There is a limit from the left and a limit from the right, but they don't equal one another, so the limit doesn't exist. And this is called a jump discontinuity. At x equals 1. Sorry, at x equals 2. All right, that is it for this section. There will be one of the problems from the chapter review that I'll come back and talk about in the next video. And then we'll start moving on and talking about material from section 2.1. So I'll see you for that very short video next time, where we're just going to do one problem from the chapter 1 review problems. See you next time.